Hello. So in this example, I want to go through in more detail um, the motion of an object which rolls without slipping. And we're going to work this out symbolically. So we'll go ahead and assume that the radius of this object is r. And what I would like to do is I'm going to assume that it rolls with no slipping. Okay, so no slipping. That simplifies the analysis. So if it rolls with no slipping, we want to find what is the velocity of the center of the wheel, what is the acceleration of the center of the wheel, and what is the acceleration at the point A. And we are going to leave this symbolic in terms of an arbitrary angular acceleration and an arbitrary omega. And what we're expecting here is that you should, because increasing these numbers, you would think would make the velocity increase, and then increasing alpha would make the acceleration increase. We expect there to be minus signs between the linear quantities and the angular quantities. So let's see how that plays out. So the way I'm going to do this is I'm first going to use an IC, instantaneous center of motion analysis, to relate omega to the velocity of g. Okay, so that's how I'm going to get that part done. And then I'm going to use the relative motion equations for acceleration to determine the two accelerations. Use omega and alpha and the relative motion equations to get AG and AA. So that's basically how I want to proceed. Let's dive right in. Excuse me. So, we know, because it rolls without no slipping, that point A is also the instantaneous center of motion, which means that the velocity of g should equal omega cross the vector from G to A. And we know it only moves horizontally here. So I really just want the magnitude. So then I know that the velocity G, or not the magnitude, sorry, the component here, I guess you could say the magnitude, yeah, is going to be omega times r. Now, where r is the geometric quantity, the radius of the disk or wheel. Now, let's worry about minus signs. I wrote it out and I said magnitude, but I didn't even put the bars there because I knew that if omega is negative, then the velocity should be positive. So I just need to put in a minus sign there. And now it's actually a true statement for just the components, not even taking an absolute value. All right, so that's the first task. Let's go through and try to figure out the accelerations. All right, so my formula for the acceleration at point G will be the acceleration at point A, the instantaneous center, the contact point, plus alpha cross RGA minus omega squared RGA. To do this, we're going to note that alpha equals alpha z hat, and know that RGA, we'll just look at that. The vector from A to G has size r and it points straight up. So that's just going to be r y hat. So this allows me to write, oh, and the other thing I know from the diagram is that point G can only accelerate in the y direction, whereas point A can only accelerate in the, G can only accelerate in the x direction, whereas point A can only accelerate in the y direction. If you follow a point on the edge of the wheel, it kind of goes down, hits the ground, pops back up. That's the motion that this point would follow if, as it goes around the wheel. And what you can see from that is at the point of contact, point A only has acceleration in the y direction. Whereas G, being at the center, can only move in the x direction. So that helps us because it simplifies things. We know that this acceleration is only in the x direction, whereas this is only in the y direction. This, well, I have to take the cross product between alpha and r, and I know that z hat cross y hat is negative x hat. So this would give me minus r alpha x hat, and this term is going to be minus omega squared r y hat. And then I want to reorder these. So I get the acceleration g times x hat equals, I'm going to pull out the r component stuff. Whereas the y components would look like this. And we see the following facts. First of all, notice that on the left-hand side, there's nothing in the y direction. That means that this must be 0. We learned the acceleration at point A, which is only vertical, is minus omega squared r in the y direction. Sorry, because it's 0, it's plus. I got myself backwards there. All right, so that means that's a centripetal looking term, okay? Omega squared r is the formula for centripetal acceleration, and it points up away from the surface of contact. The acceleration at the center of the wheel is just this, and that has a tangential acceleration kind of look to it. So notice what I said. If alpha is positive, then the acceleration is negative, and vice versa. If alpha is negative, the acceleration of the center of the wheel is positive. This acceleration always points up from the ground, and it really has to do with this kind of path dependence of a point on the wheel, such that it's only moving in the y direction when it touches the ground. And going back to what I claimed earlier, also, then notice that the velocity of point G, if I write it out with components or with vector notation, this would be minus omega r times x hat, saying that basically if omega is negative, the velocity is positive in the x direction, and if omega is positive, the velocity would be negative. And that's all compatible with standard kind of math definitions of minus signs, as well as just looking at the diagram. Okay, so that's an example, and the key points are showing that the relationship between omega r and the velocity of the center of the wheel, omega r and the acceleration of a point on the edge of the wheel, and r and alpha and the acceleration of the center of the wheel. Okay, hopefully that was helpful.